Hello students. In the last class, we learned about displacement, distance covered, velocity and speed. Now, before we move further, we must pause a little to learn a bit of an important topic in mathematics called calculus. We use calculus extensively in physics, so it's important to get a good understanding of it right at the beginning. I'd therefore suggest that you learn it well from a good mathematics textbook of your choice. I'll post in the details section of this video some good links that you can refer to. Now, there are three concepts which we need to understand at a very fundamental level at this stage. They are limit, derivative, and integral. Now, let's look at each one of them. Suppose we have a variable y which depends on x mathematically. We call this relationship between y and x as y being a function of x and write that as y equal to f of x. Here are some examples of such functions. Y equal to 2x plus 3x square plus 5. Here's another example. Y equal to sin x plus 8x plus 7x cube, and so on. Please note that there are only two variables here, y and x. The rest are constant numbers like 2, 3, 5, 8 and 7, which are all constants in these equations, or operators like sine or exponents of x like 2 for square and 3 for cube. Please note that we will be using the terms y and f of x interchangeably in this session. That is, y is equal to f of x. X here is called the independent variable and y is the dependent variable. That means the values of y can be obtained by substituting any value for x. Now, with the condition that the expression on the right hand side in x is defined for that value of x. Why do we need that condition? Now let's look at an example. Suppose we have f of x equal to 1 by x plus 3. We can show y and x graphically by plotting y versus x on the rectangular coordinate axis. Now, just a side note, the rectangular coordinate axis mean the x, y and z axis that we so often talk about, where each axis, that is x or y or z, is perpendicular to the other two. As you must have noticed from the way f of x is defined in terms of x, we cannot obtain the value of f of x for x equal to 0. Because dividing by 0 in the expression in x on the right is not mathematically defined. Therefore, we can say that y is not defined at x equal to 0. Unless, of course, we define f of x further such that we explicitly choose to assign a value for y when x is 0. Or we choose to have a different expression in x to define y at that point. Something like this. F of x equal to 1 by x plus 3 for all x not equal to 0 and f of x equal to x plus 3 for x equal to 0. The limit of a function y equal to f of x at a certain value of x is the value that y approaches, that is, gets closer and closer to, as the value of x gets closer and closer to the target value. Just think about it for a bit. X approaching a particular value, say a, can happen in two ways. Either x increases from below a to reach a, or x decreases from above a to come down to a. Therefore, the limits for y as x approaches the target value can be expressed in two ways. One, with x approaching a from the lower side, which we indicate as x tends to a minus, and the other with x approaching a from the higher side, which we indicate as x tends to a plus. The limit of f of x at x equal to a is said to exist if its limits as x tends to a plus and as x tends to a minus both exist and are equal. For example, if we look at our earlier function, the value of the function approaches 3.5 as x approaches 2 from either side. The limit of the function at x equal to 2 is therefore 3.5. Now, it's possible that y may not actually be defined at x equal to a, like we earlier talked about, or that the value of y at x equal to a is different from the limit of y as x tends to a. In such cases, the function is said to be discontinuous at x equal to a. In this chart, We know that y is not defined at x equal to 0. But what about the limits as x approaches 0? As x increases from the negative side, the value of the function dips down and gets closer and closer to minus infinity. So, the limit of f of x as x tends to 0 minus is minus infinity. And as x decreases from the positive side and approaches 0, the function spikes to plus infinity. So, the limit of f of x as x tends to 0 plus is plus infinity. And since these two limits are not equal, we would conclude that the limit of the function at x equal to 0 does not exist. Now let's move on to derivative. For y, which is a function of x, the derivative with respect to x is defined as the ratio of the change in y to the change in x, with one key thing. The change in x is very, very small. That is, it's extremely small and close to 0. Now, calculus often seems like a different language in itself, so it's important to get the terms and symbols right. Since we understand limits now, here's how we would read it. F prime x, which is a way to denote the derivative of x, is equal to df of x by dx, which is another way to write the derivative of f of x. And since f of x is equal to y, we can write that as dy by dx equal to limit of delta y by delta x as delta x approaches 0 or delta x tends to 0, as we also say it, equal to limit of f of x plus delta x minus f of x, which is, in other words, the change in the value of f of x as the value of x changes by delta x. And this change divided by delta x as delta x tends to 0. Now, since y is equal to f of x, df of x and dy both mean the same and stand for changes in y when x changes by dx. The prefix d is to indicate that the change in x is infinitesimal, and we then have the corresponding change in f of x or y. So, to repeat, dy by dx means derivative of y with respect to x. Also, dy is the change in y when x changes by dx, considering that dx is infinitely small and close to 0, which is what the expression in limit says, that is, limit of delta y by delta x as delta x gets closer and closer to 0. Here are derivatives of some common mathematical functions. The derivative of x to the power n is equal to nx to the power n minus 1. The derivative of sin x is equal to cos x. The derivative of cos x is equal to minus sin x. The derivative of tan x is equal to sec square x. The derivative of a constant c is equal to 0, which is because a constant will never change even if the value of x changes. The process of finding derivative of a function is called differentiation. The reverse operation to differentiation is called integration. Suppose g of x is the derivative of y, that is f of x, and we must mention that it's a derivative with respect to x. The method to find out what is f of x when we are given its derivative g of x is called integration. So let's start by writing g of x as follows. G of x is equal to df of x by dx. Multiplying both sides of the equation by dx, we get g of x dx is equal to df of x. The operation of integration is shown by using an operator that looks somewhat like a tall and narrow s, and which is called an integral. So this is how we read it. Integral of g of x dx is equal to f of x plus c. Now the reason we put a constant c in the end is because the derivative of a constant is 0. Therefore, whatever be the fixed value of c, if we differentiate the right hand side of this equation, we will get g of x. That is, df of x plus c by dx is equal to df of x by dx plus dc by dx, which is equal to g of x since the derivative of a constant is 0. Now c might as well be 0, but we don't know when we are only given g of x and are asked to find the function which when differentiated gives us g of x.
Please note that integrals and differentials are additive, that is, dA plus b by dx is equal to dA by dx plus dB by dx. Similarly, integral of a plus b dx would be equal to integral of a dx plus integral of b dx. The integral of the form integral of g of x dx equal to f of x plus c is called an indefinite integral, as it just gives the parent function in terms of x, irrespective of the values of x. If we want to find out the change in y, that is f of x, when x changed from x1 to x2, given the derivative function g of x, the calculation for that is called evaluating a definite integral. At the bottom of the integral operator now, we show the earlier value of x, say x1, and at the top we show the later value of x, say x2. So our definite integral reads as follows. Integral of g of x dx with limits x1 to x2 is equal to the difference between the values of f of x plus c when x is equal to x2 and when x is equal to x1. C cancels out in the process, so it doesn't matter what the value of c is in the first place. So to calculate the definite integral, we basically evaluate the indefinite integral and then find the difference in its values by substituting the upper and lower limits of x, that is, the values of x after and before the change. Here are some common integrals placed alongside the examples of common differentials. Integral of x to the power n dx is equal to x to the power n plus 1 divided by n plus 1 plus c. Integral of sin x dx is equal to minus cos x plus c. Integral of cos x dx is equal to sin x plus c. Integral of sec square x dx is equal to tan x plus c. And integral of 0 dx is equal to c. And we know that is because the derivative of a constant is 0. Now let's get back to talking some physics and see some of these mathematical tools in action. We saw in session 1 two ways to describe how fast something moves: average velocity and average speed, both of which are measured over a time interval delta t. However, when we say how fast something is moving, we refer to how fast it is moving at a particular moment in time. Like when you're driving your bike, the speed that you see in the speedometer is the speed at the moment you see it, and it keeps changing based on how much you turn the accelerator. This velocity or speed at a particular moment is the object's instantaneous velocity, or v. When we just say velocity, it's the instantaneous velocity that we are talking about. Mathematically speaking, instantaneous velocity can be derived from average velocity by shrinking the time interval delta t over which we are calculating the average velocity closer and closer to 0. As delta t becomes smaller and smaller and gets closer and closer to 0, the average velocity approaches a limiting value, which is the velocity at that instant of time. We represent that mathematically as limit of delta x divided by delta t as delta t tends to 0. Do you recall what we learned a minute ago? Let me reiterate. If the position x is a function of time t, that is x equal to f of t, the ratio of change in x, that is delta x, to change in t, that is delta t, is what we defined in session 1 as the average velocity of the particle. In finding this ratio, if we shrink delta t so small that it is infinitesimally small and closer to 0, that is, as delta t approaches or tends to 0, the ratio delta x by delta t would approach a limit, which will read as limit of delta x by delta t as delta t tends to 0. Does this ring a bell? The limit is exactly what we call the derivative of x with respect to time. So in other words, the instantaneous velocity v would be defined as v equal to dx by dt, that is, the derivative of x with respect to time t. We can omit the word instantaneous here and just call it velocity. Velocity is another vector quantity and thus has an associated direction. Speed, on the other hand, is the magnitude of velocity. That is, speed is velocity that has been stripped of any indication of direction either in words or via an algebraic sign. Let's try to understand it graphically and through an example. Let's consider that for an object moving in a straight line, its position at any point of time t with respect to a certain reference point on that line is x. Remember that time t is also with respect to a reference starting point in time when t is 0. Say, we can start recording time setting it at 0 at the moment the object starts moving. Now this functional relation between x and t could be of any form. But for the sake of simplicity, let's say it is x equal to t square. Here t is the independent variable and x is the dependent variable. And x is a function of t. Let's plot x against t. So graphically, at any time t, we can find the corresponding x from this curve. Suppose at time t1, the position of the object is at x1, and at time t2, the position of the object is at x2. So over this time interval, we have delta x equal to x2 minus x1 and delta t equal to t2 minus t1. If we want to find the instantaneous velocity at t equal to t1, we need to squeeze delta t to so small that it is very close to 0, and t1 and t2 are almost the same. If we zoom this little triangle that gets formed between the 2 points on the curve corresponding to the 2 positions of the object, what we get is a right-angled triangle. The sides of the right-angled triangle would be delta x and delta t. As delta t gets closer and closer to 0, delta x will shrink in length and move left. The points A and B will tend to converge, and the hypotenuse will in fact become a tangent to the curve at the point A. And what will be the slope of the tangent? In case you're not aware of the concept of slope, it is the trigonometrical tangent of the angle a line makes with the x-axis. So the hypotenuse makes an angle theta with the x-axis. The slope of this line, therefore, is tan theta. By trigonometric definition, tan theta here is equal to delta x by delta t. For AB to become a tangent to the curve, that is, touch the curve at a single point, A and B should converge. And like I mentioned earlier, for that, delta t should tend to 0. So going back to our dear friend, the limit, we have tan theta equal to limit of delta x by delta t as delta t tends to 0. And that is equal to the derivative dx by dt, and which is equal to the velocity v. Okay, so we ended up proving a property of the derivative, which is that the derivative of a function at any point is equal to the slope of the tangent at that point. Besides, of course, in this specific case, we have seen how velocity at a point is equal to the derivative at that point of the position time curve, and that this instantaneous velocity can be derived as the limit of the average velocity over a time interval delta t as delta t tends to 0. For the specific function that we considered for making this graph, x equal to t square, what would be the velocity at t equal to 2 seconds? Velocity, as we know, is equal to dx by dt, and in this case it would be d by dt of t square. We mentioned earlier that d by dt of t to the power n would be equal to n t to the power n minus 1. So velocity here will be v equal to d by dt of t square, which will work out to twice of t, and that will be 2 into 2, that is 4 meter per second, assuming all distances are measured in meters here and all time in seconds. Well friends, that was a lot of mathematics for this session. I'd request you all to study and practice some basic calculus. You have time till the next session to get up to speed with it. You can refer to some of the links I've posted along with this video on YouTube. We'll come back for the next session and look at some more application of these tools and move further with our study of motion. Thank you all and enjoy learning physics.